Science for Future question mark. Your stage, your talk. Here we go.
Okay. Thank you very much. Okay, this is not just my talk. This talk has a history. I have a co-author, Martin Dörnkamp, is a colleague of mine who could not come here, but so I will give this talk by myself, but we worked together over the year on this talk because this talk has a history. It's a bit of the history of Scientists for Future, which is an association of scientists that evolved this year, basically with the movement of the students and people of Fridays for Future, and they were questioned, you know, that they took to the street and said, hey, we want a future, we want that things change, and they demanded for politics to change. And this did not directly happen, but it was questioned, so some professional politicians said, well, they should leave it to the professionals. And that's the point where actually a lot of scientists, and a lot of scientists I know, where they were all really mad at this, because they've been doing science and research for so many years. And we've been, I mean, I don't know if you saw the presentations before, and how much effort is being put into this research to make it better and better models. And what I will show you, this presentation is about the results of the outcome of this and what this means. And still nothing changes. So they write papers, they write reports, and, well, nothing happens. And so the only thing we could say was basically, hey, they are right. Things need to change. And that's why we got together and formed this association. So there's a charter on this which says basically what we do is we go out and we try to inform people on the research, on the state of the art of the research, and how things are currently. And that's why I'm here. So that's exactly what I'm doing here. So we go out to wherever, and you can come to us and ask for presentations, for discussions, to get informed on this topic, on what does this climate change issue actually mean. And this is the disclaimer now. I can tell you this is not a good mood talk, okay? So this, this is a bit, because the topic is very serious. So it's a bit different than I usually do it, so in the end it will look a little bit better than in the beginning, but nevertheless. So where are we currently? So this is the current graph. It's also from the, this is all not research by myself, this is mainly from IPCC reports, and this is from the report from last year on the 1.5 degree report, which was basically done or put together because in the Paris Agreement in 2015, it was said, well, the world, or the governments of the world want to keep the climate change to the temperature change to well below 2 degrees, if possible, to 1.5 degrees. And the question was, hey, is this actually possible? Can we make that? What do we need to do this? And so there has been a lot of questions about this, and a lot of research, a huge number of publications came out on this topic. Hey, what does it mean to have a 1.5 degrees warmer Earth? What does it mean to have a 2 degrees warmer Earth? And is this actually possible to limit climate change to these temperatures? And this is the current state. So this is, I really love this graph because it contains a lot of different things. So what we're talking about, so we have a pre-industrial period that we use as a reference. So that's the period from 1850 to 1900 here. This is the reference period where we say, okay, this was pre-industrial temperature. And everything afterwards, the changes from that are all referring to this. So 1.5 degrees or so would be the difference from this period. And then what climate does, it's not always constant. So every year you have, sometimes it's a bit warmer and sometimes a bit colder. So what you need to do is you need to average. This is quite important because then, for example, there is this year of, where is it here, 1998. there was a very warm year, and afterwards, for a long period, there weren't so many warm years, and then there were some people saying, oh yeah, look, the temperature does not change anymore, so everything's fine now. And this is of course not true, because you have to look at average periods. So the red line, this is the so-called floating average, so you always average with the years, and this gives us about the current temperature change. And so this would be like a typical climate period, which is like 20 years. So you usually look at 20 years. But the problem we have currently is that the change is so drastic that looking for 20 years, then you would always have to go far back to periods when, well, there was a big difference to today. So the last changes in this report were taken from this 2006 to 2015 period. And the extrapolation from this was basically that in 2017 we probably reached a 1 degree increase in temperature on a global scale. This is not always in the same. In different areas it might be warmer, and different it's colder, but it's the global increase. So, so this is where we are currently. So we have an increase from 280 parts per million in CO2 to about 410. This is changing. This is not constant, but it's a bit going up and down, but it's about 410 in 2019. We have a strong increase in temperature globally, but the biggest increase is actually in the winter. It's in the Arctic. And there's current Anthropogenic surplus is about 40 gigatons per year. So 40 gigatons that was actually current. This is already gone, because we're now a bit higher than that. But this was the average period from 2011 to 2017. Okay. Now I go directly into this IPCC report from last year. This 2018. In chapter 2, there's this table. I love this table. This table contains a lot of climate science, because it goes into how much actually can we further emit to reach which temperature change. So this would be here the 1.5 degrees Celsius. This would be 2 degrees Celsius. And then you have probabilities. How likely you can avoid this, or is it going to come? So if you want to avoid with a 2 sigma, that is like a 67% probability to go over 1.5 degrees, we have 420 gigatons to emit further additionally into the atmosphere. 420, as you remember, it's 40 gigatons per year. And this was, I think this was, since this is from last year, this refers to basically 2017, so this already 2 years gone since then. And it has not decreased, but increased actually. And then there's a lot of different, if you go for a 50% chance, you can say, okay, it's a bit more we can emit, and if you go with, well, we just want to have a 1/3 chance, then we actually would have double the amount we could emit. For 2 degrees Celsius, this is far more, so it's more than 1,000 gigatons of CO2 equivalents to emit. Now, there are, of course, a lot of uncertainties, all kinds of uncertainties that go with that. And one is, for example, the so-called Earth system feedback. That is, the Earth itself responds to this emission and also emits CO2 or also methane, and this has also a long-term impact. And then there are further uncertainties, and these are, this has been also part in the previous talks, that of course climate models do have uncertainties. Nevertheless, if we take this into account and say, okay, we want to avoid 1.5 degrees Celsius increase in temperature with a 2/3 probability. So they call this likely in this report. So it's likely that we are not exceeding 1.5 degrees. We have 420 gigatons surplus CO2 to emit into the atmosphere in total. 100 gigatons will be more or less gobbled up by the Earth response. This was in the report. Current research shows that this is likely a bit too conservative, so it's probably more. But, well. Okay, so our emission is about 40 gigatons. So the planned CO2 emissions by coal power plants that are running was at that period 200 gigatons CO2. So they are built, they are running, 200 gigatons by that. And then we have 100 to 150 further gigatons for planned coal power plants or those under construction. If we count this together, we have already exceeded the 420 gigatons CO2. And this is, of course, one reason why these coal power plants have to be shut down. But they're, of course, not the only source. They're only one source of CO2 emissions we have in the atmosphere. And to make this clear what this means, and this is what I go into this now, what does this mean, this 1.5 degree difference to 2 degree? And there's been a lot of research on that, okay? Now the first one is, for example, first example is here on the Arctic. I mean, there's been a lot of talks about ice barriers and so on, but of course this is not the only thing to care about. It is quite crucial that there is ice there, also because the ice, we had this before in the previous talks, that the ice reflects the sun, and the less this reflection is there, the more warmth is being taken up by the Earth again. So we have like a feedback system there. Also, of course, because of all the, it's not just the ice bear, there's like a whole biosphere there, and this biosphere has to somehow survive. Now, the likeliness of an ice-free Arctic is this graph here, of the comparing 1.5 degrees, this is this one, or these two studies, these are two studies here, one with a dotted line and one with a full line, and 2 degrees. And this is how likely is this in a certain period of time that this happens. And so you can see, if we consider again that it's likely, it's about 45 years it takes for, at a 1.5 degrees Celsius increase, that we have an ice-free Arctic. So this is actually possible with this increase, but it's like once every 45 years. If we go for a 2 degree increase, this is once every 10, or even with the other study, it's more like once every 5 years that this is happening. And this is quite frequent, and this, of course, causes quite some impact on everything that lives there. Now, this is ice in the Arctic. There's not so many people living in the Arctic, so there's a lot of further studies that have been done. And this, for example, for Africa, I will only, because of limited of time, I can do this talk for many hours, actually. I will only go on to this example here, extreme heat with record temperatures over close to 50 degrees and actually even increasing that. That has been there in 2009, 2010, in the month from December to February in Africa. And these are temperatures where people cannot be outside anymore at these temperatures. It's just too hot. And then I have, it's showing these curves, and these are probability density functions. So these curves show how often, like, each of these balcons, I don't know, bobs here are showing how often does this happen. And so here we have current, that the current status is the temperature from 2006 to 2015. That's what they call current. So there is already this increase in temperature. Under these conditions, this happens maybe twice every 100 years. If we go for 1.5 degrees increase, that's the blue line, we can see this is going to happen every more or less third year. If we go for 2 degrees, this is going to happen even more often. So this is, for people living there, it's getting hard to live there. It's just the temperature, only that. If we go for example, for Australia as an example, there we have the same, it's always these curves here, extreme warm temperatures, well, that's very easy. But in Australia, what's also important there, it's the temperature of the water, because of the corals that live there. And hot water leads to coral bleaching, so basically the corals die. And this is all, of course, as you've seen, the temperature is not always every year the same, but there was this hot summer and an extreme coral bleaching here, temperatures situation here in the summer in 2012, 2013. And how often does this happen? And we can already see here, this would be the natural, so this would be the pre-industrial curve here, where this very warm temperatures hardly ever happen. Well, we can see here already this would be every third year, currently would be every second year in 1.5 degree scenario, and probably 2 or 3 years in a 2 degree scenario. And this, well, what this means, I will go on to this later. This is an example for Europe, how often things happen. I don't know if you, I always remember that one because I was a lot outside during that period. That was a very warm summer we had in 2003, and a lot of people died of that because of the heat. And I remember being in Cologne at the time and laying outside at 40 degrees, and I was ill, and so I had 40 degrees, so outside was 40 degrees, was very warm. And so naturally this can happen, it could happen like once every 100 years. Currently we have like a situation where this would be like every 4th year, and this increases then to more than 59% of all the years with 2 degrees Celsius. So we're gonna get hot summers. This is the prediction of this study here. Well, what does this mean? Well, and now I go back to the IPCC reports, and the IPCC reports are very diplomatic always. And so they have reasons for concern, and we are all very concerned. This sounds very nice, but of course there's some background to this. So they have, in the summary of this IPCC report from 2018, they have 5 reasons for concern. That's one is unique and threatened systems, like corals, extreme weather events, and you can see that does make quite a difference from now and going to warmer temperatures. Up here we have the 2 degrees, so you can see between 1.5 degrees and 2 degrees, that does make quite a difference. Distribution of impacts, that's actually basically this means that those who suffer most have contributed less. And that's of course bad, because those who contributed most, well, don't suffer as much, and then they won't change, and that's a problem. That's why they're concerned on this one. Global aggregate impacts is basically money impact. So how much does this cost in the end to cope with the outcome of this? And well, it costs billions of dollars in the end to have a difference between 1.5 and 2 degrees every year, just to cope with the impacts. And then we have large-scale singular events that could be something like de-icing of Greenland or something like that. Well, when it's gone, it's just a singular event because then it's gone. This is very abstract, so they get a bit closer to that. So warm water corals is basically, they're having already a problem. Well, I will show this later. Well, they expect about 90% will die off at 1.5 degrees. Well, they will die out at 2 degrees, most likely, certain. And this is, of course, this is well, it's important for nourishment and for people who live from the sea, from whatever they fish out of the sea, because in corals there's a lot of, it's like the childhood bed of a lot of fish. So they have we do get quite an impact in the end of on fishery. This is why this is so red. Mangroves also get an impact on that. There's about the same story, so a lot of small fish grow up there. Well, the Arctic region is getting increasing problems with the ice. Well, these are all kind, I will go into this later. Coastal flooding will increase from 1.5 to 2 degrees. This is, well, flooding in rivers and so on. Well, and we will get some more heat-related morbidity. Now, there's been a new report this year on land use, and this has been even more into this now different scale. Please watch that. So, where am I here? So the scale here is going up to 5 degrees, and if you look for that, yeah, so it's a bit different. So the lower ones, 1.5 and 2 degrees, are in there. But problems they see is a dry land scarcity and water scarcity in dry lands. So that's desertification, a lot of that. Soil erosion, which is related to that. Vegetation loss is also related to that. Vegetation loss is, yeah, I will come to this later. The wildfire damage, we can see that already today. I mean, in the news, like now it's Australia and Chile, but before it was more California and so on. So this will go on. This is no coincidence that this is happening. We have permafrost degradation. We have tropical crop yield decline. Well, crop yield is, of course, that hurts because, well, this leads, of course, in the end to food instabilities. And we can see it does make quite a difference already between 1.5 and 2 degrees, but of course it can get worse. And they are more specific on that, what they mean with this. For example, in wildfire damage, they expect an increase in fire in weather season currently, over 50% increase in the Mediterranean area if it gets above 2 degrees. And, well, if we go to 4 or 5 degrees, they expect, well, hundreds of millions at least, or over 100 million people additionally exposed. In terms of food supply instabilities, well, what we already see is, well, we have like spikes in the food price. This is not so important for us usually, but of course for people in the world that don't have much money, and we still have almost, it's not quite 1 billion people in the world that live off less than $2 a day. For such people, this is of course quite important. If we go closer to 2 degrees, they do expect periodic food shocks across regions. So basically that there will be situations where there will be no food available anymore. If we go up to 4 or 5 degrees, this would lead to sustained food supply distribution problems on a global scale. So this depends on what kind of scenario we are calculating. I will go into this later. One additional thing is also to think of that we are not only talking about the temperature. Also, the water of the oceans take up the CO2. They take up a lot of the CO2 that we blow into the air. And this leads to an acidification. And so the pH value of the oceans, they decrease. And this has an impact on a lot of animals that build up calcium carbonate. So shells, basically. So all kinds of bivalves, all kinds of like cancers and all that, they depend on building up this calcium carbonate. And if they're not able to do this anymore, of course, they don't grow anymore, and they are pretty much in the beginning of a food supply, a food chain in the oceans. Now I was reading this 2018 report, and somewhere there on page 223, I found then this here, where they basically say, okay, we do have this impact, and there is this aragonite saturation, which is, well, basically that's a point where this build-up for a specific animals is not possible anymore at this saturation point, because the chemical reaction does not work anymore. And this depends on the temperature, this depends on the pressure, and the higher the pressure is, the earlier this point is reached, also the colder the temperature is. And so this is what you can see here on the right-hand side. They investigated this mainly from the pole regions on, and so that this point where this point is will reach the surface of the ocean from 2030 onwards, so that all these animals on the surface of the ocean are not building in the polar regions, will have problems to build up actually their shells anymore. This has two different impacts. Of course, one impact is they don't grow anymore. This has a big issue on the food chain in the oceans. The second impact is actually that this was one of the carbon sinks. They took CO2, and with calcium they build up these shells, and they die off at some point, and they sink to the ground, and well, the CO2 is gone. Well, if this is not happening anymore, of course, this type of carbon sink does not work anymore. Okay, now I've talked a lot. These are further. I will skip through this quickly. These are all kinds of things that happen, and so in this 1.5 degree report, they compared for a lot of regions what will happen. So for 1.5 degree warming or less, of 1.5 to 2 degrees and 2 to 3 degrees. And there's all kinds of things. This is a big table in this report in chapter 3. Read these reports, please. Read these reports. They're good. And they're actually scientifically good. I mean, it's in terms of if you do science, it's really, really good. Because they have so much literature and so many cross-references, and how they do it to be very sure to say, okay, this is what we can say with this certainty. This is very, very good science, I think, at least. Okay, so I will not go into all of this, but it has to all kinds of regions severe impacts, like Southeast Asia, for example. They have, this risk of increased flooding, and they have increased precipitation events, and yes. And, well, I think the most significant of this is the significant risk of crop yield reductions, which is avoided if we stay below 1.5 degrees. If we're not staying below 1.5 degrees, they say here, they estimate 1/3 decline in per capita per crop production per year. 1/3 less food. That's not good. And if we go even higher, well, this is getting worse. For small islands, the small islands are well known, of course. The sea level is rising, so they have a problem. And actually, the main problem they have is not that just the water is going over their island, but that the salty water is rising and is intruding the freshwater reserves they have. So they get a problem with fresh water. And, well, this is already a problem for them for 1.5 degrees. For 2 degrees, it's like a very severe problem. And that's why they are pushing so much for the 1.5 degree change maximum. In the Mediterranean, this is very close to where we are currently. So they expect a reduction of runoff water, so this is in rivers, of about 9%. It's very likely. Well, there's a range given, as most of the time they have this. So there is already a risk of water deficit at 1.5 degrees increase in temperature. If we increase further, we reach about up to 2 degrees, we have about 17% less water in the rivers. This is, of course, not good. I mean, especially, okay, in Germany, for example, there's a lot of food coming from Spain, and they do already have a problem with their crops, with water for the crops. And this is getting worse. West Africa and Sahel, well, there is the prediction, of, less suitable land for maize production by 1.5 degrees already, by 40% less land. 40%, that's a lot. It's not the region where people already have a huge surplus in food every day. So there is an increase in risk for undernutrition already for 1.5 degrees aim. If we increase, this is just getting absurd in a way. It says higher risk for undernutrition, of course, because it's going to get worse. Apart from this, that it's too hot to go outside anyways. For Southern Africa, it's similar. It's not as drastic, so there is already the high risk for undernutrition in communities dependent on dry land especially, so savanna areas which are rather dry. And this is getting worse again. Well, in the tropics also there's a risk to tropical crop yields, we already heard that. And on the other side it's also there these extreme heat waves they're going to face. So this was like a table in there with a lot of details of what they expect from 1.5 to 2 degrees. Now, what scientists are a bit strange sometimes because they're also then doing their science and they look at different things. And one thing they are actually now worried about, and this is actually, it is worrisome, very worrisome, is that actually, climate change has been always there because there has been like a cycle, and this is the so-called glacial interglacial cycle. The Earth has been going through. This has to do with the position to the sun and a lot of feedback systems that kick in. If you cool the Earth, you have more ice buildup, then you have more sun being reflected again, you have less energy that stays on the surface of the Earth, and then it gets colder and colder and colder up to a certain point where this changes again and goes back. And this has been going on for hundreds of years, and the point is now we've left the cycle. And this is the part that's shown up here, that basically we are now on a completely different trajectory, and that's the trajectory that is we're heating this up, and the Earth is responding, and it's also heating itself up. And so we are on a path, and it's not quite clear, so they show this graph here. There is actually the possibility that the Earth will go on this path to heat itself up without us even. And this is called tipping points. So there are several things that happen there. That is, for example, the melting or thawing of the permafrost. There is methane hydrates in the ocean stored that might be triggered to evolve. There will be a reduction of CO2 intake in the oceans. Currently, a lot of CO2 is taken into the oceans, but this will get less and less the more saturation comes in there. We have a die-off of rainforests. So, last summer we've seen that there were a lot of rainforest burning in the Amazons, but this will also happen by the increase of temperature without human impact. And in this paper here by Stefan and some others, they said they estimate of about a rainforest reduction of up to 40% by an increase of up to 1.5 degrees anyways. So we're gonna lose rainforest, a lot of rainforest already like that. We have a die-off in the boreal forest. This was the summer in Siberia. Well, they just don't die off, they get burned, and there are other reasons why they die. And so there's a lot of CO2 going to be emitted from forests that are where carbon is stored currently into the atmosphere. We have a reduction of ice and snow, so there's more reflection of the sun, less reflection of the sun into the atmosphere again. And we have a reduction of ice volume, so we have an increase in sea level. And this whole thing, this is like a communicating system. And one thing triggered will trigger something else. This is sometimes goes by circulations, also by ocean circulations and so on. So one thing can trigger the next thing, and this might trigger the next thing, and this will go on. And if this happens at a certain time, at a certain intensity, then we will not have, as human beings, with the current technology we have, we will not be able to stop that. And that's what they are worried about, so this climate scientists, that we should not get these tipping points to go too strong. They are already, these are processes that can be already seen, but well, currently they are on a level where it's bad. There was actually 4 weeks ago this paper published in Nature Climate Change where they said, well, we might be wrong with our estimation here with this 100 gigatons because these tipping points are worse than we thought. So we are actually further there, more on the upper limits of the bounds where we thought it would be. Yes, so these are very worrisome situations. Now, this should trigger us to do something about it, and that's actually the point. So things need to be done, but up to now, well, things have not been done. But this is like the climate greenhouse gas emissions curves from 1970 to 2010, and we can see that not only the curve has been increasing more or less the whole period, but also the increase has increased from 2000 on. And the main increase here is by CO2. The other gases here is methane, there's nitrogen gases up here, and well, there's CO2 from, well, agriculture, forestry, and land use. This is here. They are more or less constant. Sometimes there are spikes like this. Most likely this is like rainforest burning. The only year in the recent years where there has been a decrease also in the CO2 emissions was in the economic crisis in 2008, where there actually was a decrease by 4%. Now, nevertheless, the scientists went on and said, okay, let's calculate. How can we manage to get to 1.5 degrees? And there are different scenarios. Some say, okay, let's get to 1.5 degrees. Some say, okay, maybe we need to get higher to a higher temperature and later on change that again to get to 1.5 degrees. So there are all kinds of scenarios that you can calculate. Now, if we say we use, this is CDR, I will go this carbon dioxide removal. We don't have that. And we say we use an exponential curve. Each year we reduce the same percentage of our emissions. And we want to get to 1.5 degrees. And this was the curve from 2018. In so we should have started this year to reduce our CO2 emission by 18% each year globally, 18%, if we want to reach 1.5 degrees. If we want to reach 2 degrees, it's still 5% each year. 5%. If we do this for Germany, by this, and I think this is the most important figure, it's not as important, like politicians always say, oh yeah, by this year we want to reduce our emissions by 50% or something like that. But this does not tell you what happens like by 2030, what happens until 2030. Right? So it's very important to keep in mind that it's like we have a budget. And this is actually from a paper, it's Global Carbon Budget. So they publish each year how much budget do we have left to emit. And so if we take this budget and say, okay, this is our budget, how are we going to spend our carbon budget? And this is something that we should ask all the politicians. What do you think is your budget? Why do you think this is your budget? And there's been actually an article by climate scientist Stefan Ramsdorff in the Spiegel, where he said, okay, let's estimate we have about 7.3 gigatons CO2 overall budget in Germany, and we could say if we want to reach 1.5 degrees, this would mean we continue our share of emissions, which would be in Germany, which is like double the average of the rest of the world. And we say, okay, we have the right to blow out in the air twice as much as the average person in the world, then we still would have 1.5 gigatons CO2 in Germany to emit. And how are we going to do that? That's the question. Do we have this in mind? Of course, we can calculate this down to each person in Germany, so we end up with about 40 tons per person. So each of us can also think of this. I have 90 tons here, 90 tons that is to emit. How am I going to spend this until the end of my life? Now, if we go back to this report, then we have different scenarios. And as you can see, there are different ways of doing that. And these are different economic scenarios. And you can see already that most of these scenarios do have negative emission at some points. Actually, all of them have. Some of them include carbon capture and storage, here as shown as BECCS. And depending on what kind of economic scenario you go for, this is more or less. And here it's like up to about 20 gigatons per year to be stored in the ground. The green part here, agriculture, forestry, and land use, and other land use, this also, of course, you can reduce CO2 by planting trees. This is actually a very efficient way of doing that, but of course the land area is limited, and this is also true for other things. And of course, the land area we can use is decreasing due to climate change. We should always keep this in mind. Now, the base of all these scenarios, they put this again into a table, and I put some pictures to that. So they said, if we want to reach to 1.5 degrees, what we have to do, we need to rapid and profound near-term decarbonization of our energy supply. So basically, we have to be very, very quick and change our energy supply. That's the first part. The second part, we need greater mitigation efforts on the demand side. So we have to use less and get smaller with things. Third part is, well, we do have to do this within the next 10 years. So we cannot wait. This is very, very urgent. Well, this is actually a table that looks like this a bit, sorry for that. So the main thing is that the additional reductions come from CO2 emissions because the other greenhouse gases are already included in the 2-degree scenarios. We need to invest differently, so investment patterns have to change strongly. The best options actually for 1.5 degree scenarios are the ones that go with a sustainable development. Because if people don't have food to eat, they don't have the chance to take care of the climate anymore, because first they're trying to survive. So we do have to also care about how people can live on this planet. This helps protecting the climate. Well, then they say, okay, we probably have to think of climate, the carbon dioxide removal somehow at the mid of the towards the mid of the century. So this has to be implemented now. And what we also have to do is we have to switch from fossil fuels to electricity and the end user sector. Now, CDR, carbon dioxide removal, I will say a bit about that. This is, of course, agriculture, forestry, and land use. That's very easy, planting trees. Then there's BECCS, so you use basically biomass to produce some gas, and then you capture the CO2 from burning the gas and press this into ground in carbon capture and storage. Or what you can also do is use direct air capture, as where you use, these are like these machines, so they take CO2 from the air, and then you have to store it. And you can see it's such a machine here. This was like a model at the time. So these have been already existing models. So basically, this can take 1,000 tons of CO2 per year. So if we want to go for gigatons, then we would have to build millions of these in the end. Problem with that is a bit, and discussed also in this report. So basically, we have an energy usage of that by 12.9 gigajoules per ton CO2. So basically, if we want to use put down 15 gigatons of CO2 per year by this, which was in one of the scenarios, we would need about 1/4 of the global energy supply only for atmospheric waste management. It's called like this. And the funny thing, this was like a professor, we had them at our university here in Oldenburg, and he gave this presentation. He said, yeah, this sounds so crazy, but the climate change will hurt you so much, this will be done. Yeah. On BECCS, that's a different way of doing that with a biogas. So the thing is, if we want to have that at large scale, it requires huge amounts of land use to produce this amount of biogas. And the other drawback is, of course, that you do have to take care of your storage systems to avoid the gas to come out, because, well, CO2 has a higher density than oxygen, and it stays on the ground if there's no wind. And if people live there, you don't have anything to breathe anymore. Now, there are, of course, different sectors. This for the EU, for example, where the greenhouse gases come from. So the main parts are, of course, agriculture. There's transport and the energy industry, but there's also other industries. And it's important to keep in mind that this is not equal over all different countries, but it's also distributed dependent strongly on the income of the people in the countries. So the so-called high-income countries here, they have the highest share in the CO2 emissions, while the so-called emerging countries, they're almost at the same level now, while low-income countries, they mainly have CO2 emissions here from agriculture and land use. So the question is, can we make it to 1.5 degrees? That's a good question. So there have been a lot of studies, like for Germany and the EU, either on like energy infrastructure, for example, or the whole system. There was one study from this year. They looked for 95% CO2 reduction by 2050. There was one study currently just released for the complete EU, and greenhouse gas neutral EU by 2050. And so obviously, technically, there is this assumption that this is possible. One main thing of that is that we have to go far more efficient. And one thing in that is use electricity, because electricity is very efficient in many things. So currently, the prime energy consumption in Germany is about 3,200 terawatt hours in total. And the assumption for 2050, where they have this 100% or 95% reduction, would be 1,300 terawatt hours, or by the other study was even less than that. That depends a bit on the mixture they use. The reason for that is, for example, that the efficiency, for example, of battery-driven cars is much higher than those of combustion-driven or other methods. So it really depends on which technology you put into use on how good you get. On the EU level, it looks a bit like this. So their demand and supply today, and this would be, so the reduction is not quite as large, but they still assume that we can reach this type of reduction if we want to. Nevertheless, they're not assuming 100% CO2 free, but they calculate with negative emissions by agriculture and forestry. So this is actually in these calculations, and I really like the one by Rubinius and so on. That's the lower one, because they actually calculated completely with storage systems, with electricity grids and all that, and how much needs to be invested into this. This is a very detailed study, very good one. So this is actually technically possible. And they even calculated this, what happens in the so-called Dunkelflaute, that's a German word for there's no wind and no sun in the winter, for a period of time. And what happens, and this can actually, and that's what all they assume, is that we do have a lot of storages for gas, and we can use these current strategic storages for gas in the future to store power to gas that's won by electricity there as a backup. So basically, technically, this is possible. So to conclude, so the climate system is already at a critical stage. The prospect for a 1.5 degree warmer Earth are already very bitter. And well, the IPCC reports and all the reports all of them go for we should not exceed 2 degrees, because we have this thing of the tipping points. And several reasons we already have these 2 degrees. Yeah, this carbon dioxide removal is presented, basically this is hard to avoid, but there are these critical things concerning carbon capture and storage. And whatever we need to do is we have to act fast. And that's the main thing. This has to be done very quickly. And I must say, I'm very sorry, but our government well, yes. So it is not a technical issue, it is a political one. Yes, thank you.
Bernhard, thank you very much. We do have 8 minutes for questions. So we have a couple of microphones here in the hall. Please line up over there. We have those 8 minutes. I'm sure there will be questions. The signal angel is signaling over there that we have a question from the internet.
Do you see nuclear power plants as a temporary solution to slow the emission of CO2? And we had quite some discussion in the internet. There was another one answered, you need more than 10 years to build new nuclear power plants. And the response was, well, you could get the shutdown ones back on the power line. So is that a realistic scenario in your view?
Well, there is actually, this is a current discussion going on, and the issue with that is it's not that easy to get old power plants back into running, because, well, they have a certain type of lifetime, and if you want to put them back on into the system, then you somehow would have to exceed the lifetime. And that are some, of course, some security issues, and if you want to avoid them, then you have to put a lot of money and effort into getting them to run, and you need also a lot of time to do that. And so the question is, would this be worth it? And I would say probably there are faster methods to do it. You could do it. There are, of course, the risks, and I mean, after Fukushima and Chernobyl, basically, we've all seen what the risks are. And I would say it's probably not the best and fastest way to do it. There are other ways that could be worth doing it.
Okay, then we're going to hop over to microphone number 1.
First I want to thank you for your talk. It was very informative. My question is as follows. There was a talk at the university where I studied in Darmstadt 1.5 years ago from a person who compared the IPCC predictions with what really happened with the real temperature increase and the damage which causes the climate change. And what she found out that the IPCC nearly always underestimated the effect of the temperature increase and what it causes. Have you ever heard of this criticism, and do you think this is still the case?
I hope not. The issue is, of course, that the IPCC reports is always very, very carefully taking decisions, and is very carefully looking at this, and they are more conservative and rather are lower than the actual temperatures in the end, probably because there's, of course, also a lot of pressure, political pressure on them. And so if they would predict something and they would over-predict, then people would immediately come and say, hey, you're doing panicking and so on. And so that's why it is most likely that they try to be as accurate as possible, but they rather choose the lower estimates.
Yeah, that what she was saying as well.
Yeah, I mean, in the end, it's this summary for policymakers. I showed some slides from that. That is actually voted on by governmental agents. So they bring this into a governmental round of the UN. They are a UN entity, and the governments actually say have to approve this. And so that's why it's very, very diplomatic, and in the terms of, so they're doing reasons for concern, you know. So it's, I mean, people are concerned about all kinds of things.
Thanks.
Yeah.
All right, then we hop over to microphone 2, please.
Okay, first, thank you for your talk. All good mood is gone now. And if it's mainly a political problem, do you have any idea how we can force politicians to make the right decisions now? Because what we are doing at the moment, like protesting and voting, doesn't seem to work.
Well, I think, actually, I'm very happy because I think protesting works, but it does not work in the same way that people who usually take it to the streets think it works. It puts a lot of pressure onto them, but it's one pressure on, they also have pressure from other sides, you know, and then they look at, you know, what are my voters, and if their voters are not the ones that are on the streets, well, they might be not as important. And so I think the main thing that needs to be done is to go out to the people, and this going to the street is one way of doing that, and and talk to the people, and talk especially to those who are not there on the streets yet, who are the potential voters of those who think, well, I don't have to care so much about because these are not my voters. And we just have to go out and talk. And I think this will put up the pressure together with taking it to the streets and protesting and doing whatever, talking to politicians. And I mean, we have Angela Merkel is our chancellor in Germany, and she's a physicist. I mean, she knows, I mean, she understands all this. You know, it's not that she doesn't know. It's just the pressure from the wrong side yet.
All right, and we have time for one last question. Microphone 3, please.
Yes, thank you also very much from my side for the informative talk. From the description of the talk, I was expecting more on it said something about the resilience, about climate skepticism, to be more resilient about their arguments. And I was in discussion with many other people, also climate skepticists, and what they sometimes said, they didn't criticize the anthropogenic, well, they didn't criticize the climate change at all, but the anthropogenic part of it. And what they say that there's like an increase of solar activity the last decades, which increases the temperature, and that also, like the diagram is like only from 1860, but if you consider like the last millennials, there have been higher values of CO2 in the atmosphere, but the temperature did not correlate. So how do you argue with these kind of arguments?
Yes, that's a good one. Yeah, I didn't go into these because they are sometimes the easy ones. But the thing is that I did this talk this way because it helps. If you go into climate skeptics say this, and they say a lot of different things. I could do a whole talk on what climate skeptics say. If you do that, then in the end, people keep in mind, oh yeah, there is some skepticism on this. And I did a lot of these things because by this now people can go out and say, okay, this is currently the state of the research. I did not go into the climate skeptic detailed answers. Of course, there are. I mean, I can, like for example, sun radiation is already in the climate models. The changes in sun radiations, the variations of centuries before are actually being pre-calculated in the climate models currently, because only if you're able to if you're able to mimic that in climate models today, for today or the past, if you're able to do that, then you're able to run it for the future. And this is how climate models work. And so all these variations are taking in. So I'm sorry, time is over. But we can talk about this also later on. I didn't get too much to the climate skeptics now. I'm sorry.
Thank you very much.
Yeah.
All right, we don't have time for any more questions. Bernhard, that's your applause. Thank you very much.